A source charge produces a kind of disturbance in the space around itself that affects other charged objects in the electric field. The electric field at that location is equivalent to the amount of electric force on that test charge divided by its actual charge at that location, Q sub 0. A positive source charge produces electric field lines that move radially away from this source charge. A negative source charge, on the other hand, produces electric field lines that move towards the source charge. What you see here are called electric field line patterns, and they are used to help us visualize the fields around these charges. You'll notice that for these two single point charges, these field lines are drawn radially outwards or radially inwards. For a single positive point charge, you simply draw lines that are extending radially outwards from the sphere center. For a single negative point charge, you'll see that the electric field lines are moving radially inwards towards the center of that charge. If there are several charges present, we need to find the net electric field at the various locations in space. In this diagram, you may notice that this is a different type of representation of electric fields. What we see are electric field vectors. If we were to draw the electric field line pattern, we would simply draw continuous curves that are tangent to these electric field vectors. However, there are a few common configurations you should know. For example, the electric field line pattern for two positive equal charges is shown over here to the right. Note that the electric field at the point that is equidistant from these two charges in the middle is 0. That means there's no electric field lines that are drawn in this area. On the left side, we have one charge that is positive and the other charge that is equally negative. Here we have what we call an electric dipole. The field line pattern here shows that there is an attraction between these two oppositely charged charges. There are a couple important rules that you should consider when you draw field line patterns. First, the density of the field lines is indicated by the field strength. Thus, the more closely spaced these lines are, the stronger the field is. And then as the spacing gets wider between the two lines, the field strength gets weaker. Second, the electric field lines always point away from the positive, but move towards the negative. And this is shown by these arrowheads that you see in the field lines. And third, the electric field lines never cross. There is only one net electric field at each location in space. You can't have two, say, net forces per unit charge. In many of our problems that we will be studying, you will see something called a parallel plate capacitor. This consists of two metallic plates with equal positive and negative charges. This is the easiest way to produce what is known as a uniform electric field. A uniform electric field is the same electric field at every point in that region of space. That is, it has the same strength, or magnitude, and direction. You'll notice that these field lines are all equally spaced and parallel to one another. So let's have just a quick little review once again about these important rules. First, electric field lines are always directed away from the positive and towards the negative charges. And hence, electric field lines begin from the positive charge and end at the negative charge. If you have a single positive point charge, you'll see that they move radially outwards, all these field lines. And if it's a negative point charge, the direction will flip and go inwards. If you have something that is known as a uniform field, the lines are parallel and equally spaced. And we also talked about how the field lines are stronger where the field lines are closer together. So in this region here, you can see the lines are stronger because we are closer packed together. And where the lines are further apart from one another, we have a weaker field. And lastly, another important point that I may have not mentioned earlier is that the number of lines is directly proportional to the amount of charge. So the number of lines that enter or leave a positive or negative charge is directly proportional to the magnitude of the charge. Let's see that with a simulation now. You may want to play around with some of the animations on Blackboard to see how well you're able to draw electric field line patterns. This is a diagram of an electric dipole. By sliding the charge now to be a negative charge here, here's a configuration of two negative charges. For example, try sketching the electric field line associated with the pattern of a positive 2Q charge in a single negative Q charge. After you've drawn the pattern, go to Blackboard and check your answer. Simply move the sliders here to positive 2Q and then a single negative Q, and you'll see this is the pattern you should have drawn. Notice that only half of the lines that leave the positive Q charge end at the negative Q charge. This shows that the number of lines is directly proportional to the amount of charge. Remember, this is positive 2Q, and this is only negative 1Q. So therefore, there should be twice as many lines leaving the positive 2Q charge as there is entering the negative 1Q charge. And you can play around with this simulation, such as changing this down just to a negative or two positives here. Lastly, try answering the following conceptual question listed here. Try to find 3 things that are wrong with this field pattern. We'll answer this and discuss this in class. And for your perusal, this is the correct electric field line pattern.